I wanted to just talk a little bit about what regenerative agriculture means, because I don't think there's yet like a consensus on what that actually means, and it's kind of a word that, which is a great thing that it's being thrown around now all over the place, but just kind of what I mean by it, and then maybe slowly we'll start building a consensus as to what it means, because I think that's important. We've been farming for thousands of years, humanity, and the Green Revolution happened, which is a nice greenwashing name, because Green Revolution was the seed modification, GMO. That's when that came into the scene. After the World Wars, the chemical agriculture became very prominent with the use of synthetic nitrogens and synthetic fertilizers and insecticides. And I don't know if it's true, but what I heard is that it was leftover ammunition from World War War II? Chemicals, where they were, I think it was kind of a... the ammonia. Yeah, that's it. So it was, it was some kind of happen chance where they noticed it had an impact and they needed to recycle all of this ammunition. So that's kind of where that started. So the impact that has had on our soils and on our ecosystems has been tremendous. And at some point, we realized that we were degrading the land. And so we started talking about sustainable agriculture. When did that start? Like 30 years ago? Yeah. So sustainable agriculture, and I think what was meant by sustainable agriculture is that instead of degrading the soil, we have to sustain the health of the soil. Organics came around as to separate the use of synthetic poisons and non-synthetic poisons. It had remained a very chemistry-based approach where soil fertility was all about NPK, what presence of minerals, which is very important in the soil to have an abundance of nutrients. But minerals don't have a reproductive function. They don't have a sex drive. Only living things have a sexual drive. And when we're talking about fertility, in my mind, it's, well, your ability to reproduce, right? And so this is the shift that that those of us who talk about living soils, this is the perspective we're coming from, is moving away from that it's the chemistry that's driving fertility to it's actually the life in the soil that's driving the fertility. And regenerative agriculture in that is that, well, it's no good to sustain, we can't just sustain a degraded state of health. We actually need to rebuild that fertility, rebuild the nutrient source and the resources, the richness in the soil, regenerate it. And so for me, regenerative agriculture is an agriculture that builds up richness and life over time.
I think it should be restorative agriculture.
Restorative agriculture.
We're not actually, as human beings, we are not regenerating anything. We're just trying to restore what nature put there.
Yeah. Yeah. Yeah, and
it's a different way to look at the same thing.
Yeah. Yeah, for sure. Restorative agriculture. We are restoring the life in the soil. We're restoring the ecosystem services and functions of the soil because we live on planet Earth. What does the Earth do? If the Earth is a member of our community, on a day-to-day basis. What does the earth do for our community every day? What does the healthy earth do for us every day? And what has it stopped doing for us since we've been taking away her capacity to do that? And it's, nobody fertilized an abundant forest. So the earth, one of her services is to, there's no waste. Everything decomposes and is brought back into this cycle of life. And everything becomes a food source for the next thing. So it's the cycling and turning of resources for the next thing. That's what healthy soil should be doing. Healthy soil should be providing the nutrient support for plant life. And it shouldn't be coming from us dumping piles of whatever into the system. So that's one of the functions, ecosystem services of the soil. The other is being a sponge for water. Being a sponge, instead of water not being able to enter the soil or running off, it's sunken into the soil, slowed down the movement of the water, and it's cleaned by the soil and slowly drips down, and this is what replenishes our water aquifers. This is what creates drinking water on planet Earth. And this water seeps out into our rivers. In Greek, the word river is potadi, potable. Yes, and this comes from this process. And so that's another thing that the soil does. The organisms in the soil have a big part of these processes. We've talked a lot about carbon sequestration. This is important, but if we build a giant vacuum and suck all the carbon out of the sky and don't regenerate biodiversity on the earth, we're still screwed. The aim should be to restore life on earth, biodiversity, which begins in the soil. Thanks, love. And the rest will come. And how soil is built, like what is soil? Soil, yes, it's sand, silt, clay, loam, it's air, water, there's plant roots, there's organic matter, and there's microbes. Right? This is technically what a soil is. But soil can't exist without plant life. At the beginning of time, not of time, but Earth, when the organisms crawled out of the ocean onto the rock, onto the crust, that first symbiosis that happened with the algae, the cyanobacteria, the diatoms, and the yeasts, these are all our ancestors of plant life. This is where everything begins. And this symbiosis allowed plants to colonize on Earth. And the plants didn't have roots at the beginning. It was fungi. It was bacteria. And they eroded the rock slowly and accessed the minerals for the plants who are doing photosynthesis and feeding in exchange for these minerals, feeding the microbes sugars that they were getting from photosynthesis. So transforming sunlight and carbon into sugars that they would sweat out of their body through the root system, through all over the body. We call these juices exudates. And that's what this exchange was about. And over time, plant life grew and died. And eventually, life figured out how to decompose the plant life. And so this decomposition of plants, plus the erosion of the rock, and all of that coming together with the rain, this built soil, earth. Soil is built through this process of plants doing photosynthesis, feeding the microbes in the soil who are exchanging nutrients back. This is how they feed themselves. Those plants dying, the fungi and the bacteria decomposing that, creating humus. If you pull out from under of the forest floor the leaves, and you see that dark, chewed up, very dark, chewed up leaf matter, that's humus. That's what creates that dark color and nice, rich soil. That combined with the microbes that are being fed by the plant juices in the soil, eroding the rock, extracting the minerals and the nutrients, all of this together, this is how soil is built. So, kind of like our human bodies, we're like, I don't know, we're like, what is it, 10% on a cellular level human? Something like that. The rest of us, something like that. The rest of us is other. We're a huge walking condo of microbes.
I'm a fungi.
Yeah. We're a bunch of fungis and fungals. And I'm convinced that one day science is going to discover that our whole nervous system in our brain is some kind of symbiotic fungal organism. Absolutely. Absolutely. And our whole bodily functions don't work without a good microbiome. This is what we're discovering more and more. Even Alzheimer's is being linked to gut bacteria. Our ability to have a strong immune system, our body's ability to absorb and retain the vitamins and the nutrition from the food we eat, instead of it going right through our body, which happens to a lot of people. It's our biology that is able to assimilate that nutrition. And it's the same for plant life. It's the same. They have biology all over. They're all over and within their surface and inside their tissues. Shoots, leaves, stem, bark, roots, the whole thing. And all of their ability to feed themselves, be the difference between a plant that repels insects and pests versus a plant that attracts insects and pests, all has to do with this microbiome. I just threw you guys down the rabbit hole, just a bit. Yeah.
Just to expand a little bit, you made reference to us and our community as including the Earth. Mm-hmm. In the early 1900s, Rudolf Steiner spoke about how the Earth is also a member of a community of planets and other cosmic forces, and how he could see how working with those could be helpful to making that community more visible, more understandable, and to be part of the process. So just, we are a community, but it's even bigger than us.
Yeah. We're microscopic.
Yeah, so biodynamics is a pretty interesting start for a lot of this.
Yeah, for sure. So, all that to say is like, what is soil? That was my answer. That's terrible, I know. But that's that's what soil is. And this is how soil is built on this planet that we call Earth. And that's the relationship between Earth and the water and, life being driven by life. And over these past 10 years of me looking under microscopes and all of the other people, we have concluded that the way that we've been farming and the impact of throwing even organic minerals onto the soil has been killing off some of this biology. And particularly the fungal life is depleted. Bacteria, there's tons of bacteria. You have to sterilize your soil in order to kill off the bacteria. They're very, very resilient beings, thank goodness. But a lot of the crops that we grow require also fungi. The fungi, think of them, and we're going to see this, hey, in your soil. Bacteria, they take little parts of the minerals that are eroded and the organic matter that's decomposed, and they make bricks. They make little, what we call aggregates, micro aggregates in the soil. These are like the bricks of the structure of the soil. And they do that to hide from their predators. Because once the bacteria and fungi decompose all the plant matter and all of the nutrients that were in a plant and all the minerals that were eroded from the soil, all of this is in the bodies of the bacteria and fungi. Bacteria and fungi are your bank account of nutrition in the soil. And the bacteria tend to accumulate some kind of nutrition, and the fungi another kind of nutrition. And for the plant to access that, they're not just going to give it away. They have to be eaten by a predator. So the predators of the bacteria and fungi come along and eat them. And then what happens after you eat? Well, everything poops, right? And that's the poop loop. This is one of the ways in which Mother Earth has cycled the nutrients back into other life forms. And this is how one of the ways plants feed themselves is the predator-prey interactions. And they release those nutrients now in a form that the plants can eat. Because the plant can't erode the rock itself. It can't transform the minerals into a form that it can eat without this microbial process. And so that's one of the forms. And there's also the mycorrhiza, which is a different process where they're living in. Myco is mushroom in Greek. Rhiza is root in Greek. So it's the mushroom in the roots. And they're also mining, eroding rock, feeding bacteria to erode rocks. They're also decomposing, but they're giving their nutrients straight to the plant. That's the second way. There's the poop loop, mycorrhiza. And the third way is that plants are actually farming microbes, and they will suck up microbes. They'll lure them in and suck them up into their root systems, and they'll strip them of their membranes and steal all of those proteins, and then they'll clone them, and then they spit them back out through their root hairs. It's this is life, guys. And as they spit them out, they give them a bit of food to rebuild their membranes, and they say, hey, by the way, when you come back in, I need more boron, so you might want to go get some of that. So these are the three ways in which plants actually feed themselves. It's a microbial process. And the way we've been farming has been interrupting this process. So when you give the plants everything at their feet, onto the soil, they're no longer going to use their sunlight energy of photosynthesis where they make these juices. They no longer see the need to spend that energy on feeding the microbes because they have what they need. So they can keep that energy for something else. So then you're not building this life in the soil. And then also when we till and when we put these things on the ground, we're straight up just killing these organisms. So the bacteria are making these bricks to hide from their predators. The fungi come along, they string them together, and they act like rebar in the soil. They build the structure. And we're going to see some of these megalo condominiums in the soil that Diane is building. And so every time you till, you're chopping up this rebar, and you're collapsing the structure of the soil. And in these structures that the fungi are building, that creates space for air and water. And the rest of the food web are soil animals. So there's amoeba, flagellates, nematodes, microarthropods, microinsects. And they're the ones that are going to be preying on the bacteria and fungi and having this cycle going along. Well, they need water. They need to breathe. So the fungi provide that in their structure. And they are actually aquatic organisms in the soil. They live in the water films of the soil. So this process of the fungi building these structures create the space. They're kind of the pioneer species. They create the space for all the rest of them to come and have all of the nutrients cycling. And we need to rebuild. That's why today we wanted to focus on fungi, building fungal composts and fungal compost extracts and things. There's way more things to do to build fungi, but this is what Diane wanted to focus on. And this is the urgency of rebuilding, doing fungal things. There's Michael Phillips. This is a great book called Mycorrhizal Planet. It's a fun read. It's a beautiful read. He's the one that says, do fungal things. He passed away a few years ago, pruning his apple trees. So a lot of the composts that I have looked at over the years don't actually have that much fungi in them. So there's a whole way of building composts that will actually build up more fungal life versus bacterial life. And it's not to say that bacteria are bad. It's just the need right now is to build up more fungi and to have the kind of nutrients that are cycled through fungal bodies and accumulated in the fungal bank of your soil. We need those. After years and years of trying to help farmers source compost, finally you just need to make it because the fungal compost isn't there. And I just wanted to, if this will play, I don't know if this will play. But this is what we mean by living soils, okay? The need for living soils is the need for soils that have this fungi, the nematodes, the amoeba, the flagellates, all these animals that are going to get the cycle turning. And just here, you've seen this before. You've seen this. This is a nematode. This is a bacterial feeding nematode swimming around. There's fungal strands. There's amoeba in there, flagellates swimming around in the background. But this is literally what we mean when we talk about the need for. So this is quite literally what we mean. And I like to share the microscope stuff because it becomes less of an abstract concept and it's real. Within every teaspoon of soil, there are millions. There should be millions of these organisms. So a lot of the composts, as Meg just mentioned, it's hard. A lot of them are sterile. They've been heated up too much, and a lot of them are overly bacterial. And just a quick way that you can test if you're buying compost and you want to see whether it's got some good stuff in there for you is you take 1 part compost and 9 parts water, put it in a mason jar. Shake it up really, really well for at least a minute. And then let it sit for at least half an hour. And the color of the water after half an hour, I'd say 45 minutes, if it's clear, then you have a sterile compost that doesn't even have much bacterial life to offer you, which is something. And that's a lot of the compost, especially municipal composts. And they kind of I don't know if they have to do that, but they do that because they don't want any liabilities. And then if you shake it up and after all that time the water is kind of golden color, that at least is showing you that there's bacteria and bacterial predators, and that cycle is happening. That golden color are fulvic acids, so that's good organic matter being decomposed. but we're still not fungal. And so if the color of the water is kind of brown, tan, chocolate brown, that means you have had the presence of fungi in the decomposition of that compost and their predators to cycle back around, because those are humates that you're looking at. And what I have seen is that when you have that color, you have fungi. Or if the compost was dried out too much, at least their spores will be there. And when you use it in the environment, the fungi will wake up again. What I'm referring to is when you have like a finished compost where you can't really see the organic material. You know, there might be like a bit of branch or wood chip here and there, maybe, at most, but it's finished, everything's decomposed. And when you shake that, and that, what I call that the humic acid test, the humates test, because that's a quick way for you without a microscope to know whether there is fungi in there. To grow fungi, we need carbon sources, okay? And carbon sources are, for example, dead brown leaves, not like green leaves eventually will be a carbon source, yeah. Straw, which is different from hay in that it was cut when the plant was already dead and brown before it was cut. So that's the difference between, that's straw. Hay was cut green, and even if you dried it down and it looks brown, it's still got a lot of nitrogen in there. Wood chips, ramial wood. Ramial wood is basically the chipped branches. All good. It's basically the chipped down branches. So this is what we mean by carbon source. Carbon sources are anything that have lots of structure to them. And nitrogen sources are things that have a lot of life force energy, a lot of vitality. So manures have both. But anything green, like leaves, hay, grass, weeds, food waste, all of these things have a lot of nitrogen in them. Versus when you look at like straw or wood chips, they have way more carbon. And fungi, a lot of the reason why composts are not very fungal is that they don't have enough carbon in the recipe. Like there's too much weeds and grass clipping and manure compared to how much straw, wood chips, dead leaves, grain husk, all of these carbon sources. And so I like to have at least 50% in terms of volume, not weight, of my compost pile in order to make it fungal has to be a carbon source. And now what Ruth was wanting clarity on is what happened, because there's a lot of places that have limited access to carbon sources. And this is the power of using composts and compost. I work with extracts, not teas, and I'll explain the difference later down the rabbit hole. But a lot of people are trying to build compost. Traditionally, we build compost and we spread it at large on the fields. But when we're working with large acreage and we want more fungal stuff, it's hard to get enough carbon source to make that big of a pile that you're going to spread everywhere. And so in kind of my philosophy of things is in order to have more carbon source in the fields, that's going to come from the plants you're growing. Your cover crops, your permanent cover crops, your actual crops, the animals and their grazing and all of that. So instead of planning on spreading compost everywhere to increase organic matter, that's gonna be coming from the plants and the diversity of plants and how you manage that, and if you're mulching and anything like that.
Does that improve the soil structure as well?
Of course, yes. Yeah, the plant roots that are, depending on the plants, breaking up compaction. They're also doing photosynthesis and feeding organisms through their juices that they're sweating out into the root system, and that's starting the food chain. And why we talk about diversity of plants is the more diverse your plants are on a taxonomical level. So that means, how do I explain that?
Different types of plants.
Different,
Root structure.
yeah, so it's not just species, it's actually plant families. The more diverse the plant families are, the more diverse their biology that they're growing around their root system is. And the more chances they have of working together and exchanging. So the plants will actually become a community that are exchanging resources and nutrients versus in a monoculture. Or there's people that I've seen put down like 18 species, but a lot of them come from the same family or serve similar functions, and they don't actually end up working together. So you're better off having, especially in temperate climates, like less plants, but more really different. And they end up working together and building these systems of exchange. So, and them with their roots, putting exudates into the ground, and if you're not chopping them down right away, the longer you let them grow into their vegetative state, the more and more of these juices they're putting into the ground. And those juices are organic matter. It's condensed carbon.
That's carbon? I thought if they were green, it was primarily nitrogen.
It's carbon. So they're taking sunlight, they're taking carbon molecules, and they're doing some chemistry thing, and so they're putting out oxygen. But the juices are complex chains of carbons. Those sugars are carbon chains. And that's going into the soil. And so this is how you build. It's the roots, it's the juices, and the soil's ability to cycle that, plus whatever's growing on top of the ground. That's building carbon and organic matter on a large surface, and then you can enhance that if you have a small amount of carbon that you can get on a farm, to make a smaller amount of really good fungal compost that you make extracts with or teas. So and then use that very efficiently on a large acreage, and especially in market gardening. Like you can use it at transplant, like very strategically. You can use it in your seeding mixes, but it doesn't have to be everywhere. And the plants that you grow will feed the microbes that are there. And yeah, wood chips. And you might notice that if you put fresh wood chips versus aged wood chips, you'll see a difference in the ability of those areas to soak in water versus not. So I tend to say, if you have wood chips, let it age at least one winter before using it, either as a mulch or in your compost, because fresh wood will not absorb water. And then you'll have puddly wood chip paths that are fermenting and causing problems. Has anybody seen this before happen to them? Yeah. Okay, this is a controversial topic in that the science isn't clear, but all of those, they sterilize the compost to get rid of the potential pathogens that are in the dog manure or any other manures that are in there. But the heavy metals that are in any compost, so your compost will be as good as the ingredients you put in it. It's like making a nice pie, organic pie, you know. If there are heavy metal, if there is some kind of contaminant that the animals are exposed to, that will be in their poop. if there was antibiotics, that will be not decomposed. That will be present in a compost pile. And what the literature is saying now is that or in organic agriculture, they're finding the active enzymes of antibiotics in the leafy green parts of organic vegetables. So organic greens, if they're grown using kind of conventional manure, even if it's composted, that those active antibiotics are found in the greens. Glyphosate.
That's what I was wondering too.
Yeah, so this is also where the science is controversial because things are super politicized. You're either like super for or super against, and so it's hard to trust any of the data that's coming out because some say, no, the glyphosate is broken down by the bacteria. And then the others saying, no, it's not. And I personally don't, this is just a belief. I don't think it is. I don't think it is broken down. And there's also like dosage rates and the ability of your ecosystem to deal with that. And so I don't believe it is broken down. But yeah, so whatever you put in your pile will be there at the end of the day. If you're putting things that were grown if you're putting a bunch of nettle that was grown in an area with lots of heavy metals in the soil and you're using that in your compost pile, those heavy metals are in your compost pile. So it's great for bioremediation, but when you're growing vegetables, you have to be aware of what you're putting in your compost pile. You need things to be clean. A lot of people use chicken poop straight up as a nitrogen source at the feet of their vegetables. It's a very common practice. A lot of the time, those chicken pellets are coming from conventional chickens that were fed basically McDonald's for chickens and are pumped up on all kinds of medications, antibiotics, hormones. That is in the pellets. So there's that's happening when you're using it straight. Yeah, it will produce its nitrogen, your plants will grow, but you're also introducing all of those things into your soil environment. And you're giving your plant straight nitrogen right at its feet. The plant will no longer, you're making a lazy plant. It will no longer feel the need to spend its currency of its energy that it creates every day doing photosynthesis. And it spends that energy by, it has to fight off insects, or it has to create proteins, it has to create synthesized fats. Plants are doing all kinds of things. And it's not gonna want to spend its energy on feeding the biology in the soil and creating those relationships if you're putting a nitrogen source, even if it's organic, right at its feet. So it interrupts this process. This is where having, animal manure is gold. It is gold. But the animals, you are what you eat. If you have animals that are pasture raised or fed very, very well, composting that with enough carbon inside, it's fine. It's great. It's a great source of fertility. At the feet of your plants. You're just, instead of thinking of compost as just a source of nitrogen, phosphorus, and potassium, and calcium, and whatnot, it's switching that mentality to thinking of your compost as a probiotic, chock full of life and nutrients, but it's that life that you're putting at the base of your plant to work with your plant so it can go and do all the things. And you can think of a compost pile as a source of nutrients in the sense that whatever you put in the pile, the bacteria and fungi will decompose if you're doing it properly. and have those nutrients in their reserves. So if your soil is heavy clay, and you don't want to till heavy clay, but you need to build structure. Typically, there's this thing called the calcium-magnesium ratio, and if your calcium is very low in clay compared to magnesium, the clay will stick together. And for the clay to start structuring, we need to increase the calcium relative to the magnesium, and then the clay will start to repel itself, and that's called flocculation. So if you need to do that, and you need calcium, instead of putting calcium at the feet of my plants, I would make sure that there's a lot of calcium in my compost pile that I'm putting at the bottom of my plants. Let the bacteria and fungi cycle that. And through the predator-prey interaction, as the plant feeds them and needs it, the calcium will be there. So, yes.
Are eggshells a good calcium source?
Yeah, eggshells.
What else? Fish bones?
Sorry?
Fish bones?
Fish bones, any fish waste, so fishery waste like crab shells, oyster shells, if you're near that part. We have a lot of that where we are. So this is where there's many kinds of composting, and I think today for fungal compost we'll focus on two. One of them is called the Johnson-Su bioreactor, and please write that down, Johnson-Su, S-U, bioreactor. And I'm not going to go too deep in this because if you put that in Google, you will get a step-by-step PDF of how to make these compost piles. Typically, they're just using leaves. I would use more diverse things for sure to have a bigger diversity of organisms and a bigger nutrient profile, because leaves have some nutrients in them, but it's not the same as the nutrient you'll find in a comfrey plant or in an eggshell or in a wood chip or whatever. And then the other is the thermophilic. So if you're using manure, it's the thermophilic composting, where the compost is going to heat up and you're going to have to turn it. So this is where the recipe building is. And a lot of the time, people have not been putting enough carbon. They put 1/3 carbon, 1/3 green scraps, 1/3 manure, and this is going to be a bacterial bomb, and it's going to heat up a lot. So if you want at least half of your volume to be carbon materials, so then maybe 1/3 to be green stuff, so your weeds, your hay, your comfrey food scraps, anything like that, and 10 to 20% only to be your manure. And if it's chicken manure, only 10%. If it's cow manure, 20%, horse, 20%, sheep, 15%. So if you had 10 buckets, at least 5 of those would be carbon sources. 3 of those would be green sources. And 2 of those would be manure if it's herbivore manure. If it's bird manure, you only want 1. And then I would increase again more carbon, 6 buckets, just to give you an idea. And then you keep repeating that until you have no more carbon, and that's your compost pile. You want to mix that up as evenly as possible. And like I said, if you're using wood chips, they have to be aged at least a year, because otherwise they won't decompose. And once you mix that up, you've started your pile, you need a thermometer, and you check the temperature every day. It should take about 3 to 4 days for it to reach 55 degrees Celsius. If it reaches, above 55 degrees Celsius in 24 hours, that's telling you've put too much manure relative to the carbon. And the next time you have to increase your carbon relative to how much nitrogen you're putting in there. So it should take about 3 days to reach 55 degrees, and at 55 degrees, below that, you will be composting in the sense that it will be decomposing, but you won't be treating the seeds. So if you got weeds in there, you want to treat the seeds, which is the problem that Meg was talking about. You want to be treating any parasites or anything that was in the manure, or even if you've ripped out at the end of the season your tomatoes that had a mosaic virus on it, and you still want to use that material to feed back into your system. Between 55 and up, you will be treating viruses, pathogens, disease, and seeds. Above and at 55 degrees, between 55 and let's say 64 degrees Celsius, your beneficial life, so your beneficial bacteria, fungi, all the amoeba, all the good guys you want in there, they go dormant. They can survive those temperatures. But once you get above 65 degrees and up, you start killing off also your beneficial microbes. And once you're at 70 degrees and up, you start sterilizing your compost. So that's why we get sterilized compost, is it's just heating up way too much. So you want it to be between 55 and 65 degrees. If it's at 70 degrees, what I do is I make a little donut, and what makes the temperature go up is the bacteria multiplying really quickly off of all of the nitrogens that are in the poop and in the green stuff. And it's the thermal mass, so you need a minimum of 1 meter cubed to create this heat, to have the geothermal process. If it's smaller than that, it's not going to heat up to that. So that's the minimum size you need. And so for me, if it's like too hot, I'll try just digging like a hole to reduce the mass and see if the temperature will go down. And if it goes down between to 55 and 64, then it's good. If it doesn't, then you just have to turn it right away. So the rules are, you make your pile, it's got to have enough carbon. Your carbon has to be aged a bit. And then you start checking your temperature with the thermometer. You're not looking for any temperature, you're looking for the hottest temperature. And like if this is my pile, if you're doing it on a pallet with a fencing, like the heat is not necessarily in the middle, but it's kind of right around here, the hottest. But the hottest part of the pile will move and travel over. So you're checking the temperature with a thermometer, and you're looking for it's a treasure hunt for the hottest temperature. And let's say if it's between 55 and 59 degrees, your hottest temperature, and it stays there, it takes 72 hours, 3 whole days, to treat the seeds, the pathogens, the disease, any of that. So you leave it for 72 hours. And that's how it's the temperature of your pile that's telling you when to turn it. If your pile, the hottest temperatures are between 60 and 64 degrees, it takes 48 hours to do that process. So you'll turn it in 2 days. If it's between 65 and 70, technically it takes 24 hours to do the same process. But I always try to bring the temperature down back between 55 and 64 by making a little donut, because I don't want to start killing off the good guys either between 65 and 70 degrees. And so that's how you know when to turn the pile. And you want to turn the pile in those time ranges of between 55 and 59 degrees. You'll turn it 72 hours later. It's between 60 and 64, 48 hours later. Because because you want everything to have a turn being in that hot middle. It's only the stuff in that hot middle that's being treated for the seeds, the diseases, the pathogens, and whatever. So you don't want to leave it longer. You could, but you don't want to leave it too long because the bacteria will keep burning through the nitrogen source. And you want to make it through to 5 turns to make sure you want to have enough heat to make it through 5 turns to make sure that everything has gone through this hot middle process. Yeah, so there's 2 things that are going to determine the temperature. So that's your recipe, right? How much nitrogen source versus carbon source. And the other is moisture. It's hard to, I don't use a thermal hydrometer because it can't tell you what's inside the organic material. So all your green stuff and all your manure stuff, it's all going to be releasing water. Once the decomposition process starts, moisture will be released. If your aged chips, leaves also will have moisture in it. So I don't tend to water I used to water my piles before, but then they would always leak out, and I would just wait and see. Once it reaches 55 degrees, that's your day 1 of your compost process, of your treatment process. And you can reach your arm in as far as you can go without burning yourself, but you try to go as deep as you can. I measure moisture with my hand, so you got to check temperature and then you got to check moisture. How do you know what the moisture is? You take a handful, enough that you can still close your fist around it, and you squeeze. I use 2 hands. My compost partner, Alex, uses 1 hand. He's stronger than me, and this is kind of how we do it. If you squeeze and there's water that accumulates between your knuckles but doesn't produce a drop, you're at about 40% moisture. And we want to be between 50 and 70% moisture. So if you squeeze, there's water between your knuckles, and 1 drop comes out, you're at 50% moisture. 2 drops, 60. 3 drops, 70. No water accumulating, 30. You open your hand, it sticks together, 30. You open a hand, it falls apart, 20. You open a hand and the wind blows it away as dust, you're at like 10 and under. So this is, and then, more than 3 drops, you're like 80+%. So the sweet spot for fungal compost, 50 to 60%, 1 to 2 drops.
Because it'll get too matted.
Yeah, it'll get too compact. There's not enough actual structure to keep the airflow going, and so you can't allow yourself to go up to that moisture level. So I use wood chips, ramial wood. I use straw, I use hay, and then there's bedding in my manure, and there's enough structure material that I can allow my pile to get that wet. And if you don't have that, then you want to stay around 50 to 60%. But underneath that, once it falls under 50%, there's not enough water for the microbes to do their job, and they will stop, and then the temperature will drop off. So those 2 things are driving temperature, is your actual recipe, carbon-nitrogen balance, and the moisture. Too dry, won't have enough activity. Too wet, won't have enough activity. This is the thing. With this thermophilic process, if you want to make sure, so you have a waste management pile where you're constantly adding things because you got to deal with it, that's one thing. But if you're making a fungal inoculum, you wait till you have everything and you mix it up, and then you don't add anything else once you've mixed it and made your pile. The temperature reaching a certain thing tends to only be really reliable when you mix everything all in one go and then you stop adding. You don't keep adding to it. So there's an inoculum pile where you're making a fungal compost. And this is the process of letting it reach 55, and then once it's there, and everything we just talked about, versus you have a lot of just things to deal with on the farm. That's a resource management pile where you mix as you go, but it's not as, unless you're, every time you add something, you're restarting. Because the cool thing about waiting till you have enough of everything to make a recipe and go for it is because it'll reach 55 and then you're turning. Everything for sure gets a chance in the middle and being treated for the seeds and pathogens and disease, versus when you keep adding, you're restarting every time. You're restarting every time. Food scraps get nasty if you don't do something with them right away. So this is where having a vermicompost to deal with your food scraps, or chickens or pigs to deal with your food scraps, is a kind of a whole other game. Or buy a bokashi inoculum. Bokashi is a mix of different microbes. It's a powder that you can buy. You can mix that in a bucket with your food scraps. It turns it into a non-stinky, non-slimy, powdery thing.
How do you spell bokashi?
Bokashi, B-O-K-A-S-H-I. So it allows you to deal with your food. If you don't have animals or a vermicompost, which is more animals, worms, to feed your food scraps to, and you want to keep your food scraps for your recipe, and you don't want it to get like slimy and gross, then you treat it bucket by bucket with bokashi, and you just follow the instructions on the packets, and it turns it into a shelf-stable, non-stinky, non-slimy thing, but all of the nutrients are still in there, and it's still a nitrogen source, and you can use that in your recipe when you're ready to build it. So it's just a way to like keep it, if you want to do that, if you don't have chickens to feed it to, or pigs, or if you're not just going to throw it in a pile and let it do its thing somewhere, if that's part of your richness. So it's important to check the moisture all the time as well with the temperature. You're finding the highest temperature, and you're checking every day. And this process is like 2 weeks max of you checking your temperature every day, checking the moisture with the hand drip thing. And if you need to adjust the moisture, like if it's not moist enough, wait till, let's say, the day you're turning your pile because the temperature told you to. That's when you add water, because it'll add water evenly everywhere versus just from the top, and then it tends to leak out. And if it's too wet, we always cover our compost piles with a thick geotextile so that the water, if it rains, just slides off the pile, so that we can have some kind of control over the moisture level. That's what we do. So these are the two things driving the temperature. It's your recipe and the moisture, and you want it to be between 50 and 70%. And those drops, and I'll make that available to you guys later. And you keep following this process until the temperature drops down below 55 degrees after 3 to 5 turns, and everything's had a chance in the middle. And then you want to let the pile age and mature. And this is called the mesothermal process. And this is where the fungi will come out of dormancy if you have minimum 50% moisture. And you stop turning the pile, you leave it in a place where it's not too windy. Too much wind increases evaporation, which dries out the pile. It's not too sunny. A place where it won't get flooded with water either. And you stop touching it. All you do is you check the moisture every now and then. Make sure you got at least one drop. And the fungi will keep growing and growing and growing. And if at that point it falls under the one drop, then you can water from the top. No problem. And this process, you will have a fungal compost within 6 months. If it's indoor, or not freezing outside. If it's freezing winter outside, it takes longer. If the pile gets frozen, you can insulate it over the winter. I put first geotextile, and then you can put hay. But you don't want the hay directly in contact, just because if you were managing this for seeds and you did all that work to not have seeds, and then you put hay, and then you've got that growing on your compost, you know what I mean? So you can insulate it. It might take more than 6 months still if this is happening over the winter, but you'll see. It'll smell like the earth, forest floor. You'll see that it's decomposed and ready. You might still have a couple of branches here and there, but that's okay. But this is how you make a thermophilic compost pile for fungi. And you don't have to do this for all of the material on your farm. If you've got like tons and tons of bedding to manage, that's one thing. You go, you put that in a corner, you turn it every now and then, you add whatever carbon you have, you manage it as best as you can. We're talking about making a small amount of very fungal stuff that we're then going to transform into compost extract or compost tea. This just have a small amount. So this is one way of making fungal compost.
Does it require wood chips, or can you just have leaves and straw as the carbon to make a fungal compost?
You can have leaves and straw, you can have leaves and straw, but you will be using, in that sense, maybe 6 out of 10 buckets, 60% carbon versus, it is a carbon source, but let's say the carbon-nitrogen ratio, everything alive has a carbon-nitrogen ratio. The human body, for every protein that makes up this body, has 30 carbon molecules for 1 nitrogen molecule. Okay, so our carbon-nitrogen ratio is 30 to 1, carbon to nitrogen. The carbon-nitrogen ratio of straw is like 50 to 1. Wood chips can be anything from like 100 to 1 to like 1,000 carbon molecules. So there's way more carbon in wood chips than there is in straw. And in the end, you want your pile to balance out to about 30 to 1. But if you go online and write compost calculator, there are calculators where you can put in your ingredients and it will tell you where your pile will balance out. You want it to be 30 to 1 or 40 to 1 for very fungal.
Can it be softwood, or does it have to be hardwood?
Softwood, you want to let it age 2 years minimum. The reason is that there's a lot of resins in softwood and a lot of antifungal properties in softwood, especially cedar. So you just need to let it age longer, let the bacteria nibble down the resins, and then use it. It kind of makes things, some people say it makes things acidic. So you want, but if that's the only thing you're using, for sure. But because you're using manures and other things, I found that it's okay. I was doing this in the winter. Like I stored all of my ingredients because my time of the year that I had 2 weeks to do this was in the winter. We were doing it in our big garage. So I was pallet, geotextile, chicken fencing, with another geotextile around very similar to the Johnson Sioux. And I'd have 10 buckets at a time. My recipe was 5.5 carbon, 3 nitrogen, 1.5 poops. Put that down, mix it all up, throw it in the fencing, and do that 6 times. 60 buckets is about 4 meters, 1.5 meters squared, so it's about 4 feet by 4 feet by 4 feet. Minimum is 50 buckets to make 1 meter cubed, so that's, you do your mix 5 times, and that's just for me to keep making sure that the recipe is good. It's not by weight, it's by volume. So every bucket, like leaves, I definitely pack down the leaves to fill up the bucket or the straw or the hay or whatever, versus like very fluffy and then very dense bedding with urine and manure. And yeah, so I pack that down. And even now we do windrows. We do the same process, but with our bucket loader into the trailer. And then we build the recipe in the trailer and then dump that where we're going to have our windrow, and then we keep going, and then we do our compost turner.
What do you mean by flipping? Like how do you, like what do you?
How do we turn the pile?
Yeah.
Good question. Turning is when you're doing it by hand, you're using a pitchfork, and you want to, so what I would do, oh gosh, okay, I haven't turned compost by hand in a few years, thankfully, but the idea is to get everything that was in the hot middle to the outside and everything that was on the outside into the hot middle, okay? So it's kind of ridiculous what I'm about to say, is that you take everything that was on the outside that didn't reach that temperature and you put it aside. You take the hot middle and it becomes the new bottom of your next pile. And as you're turning, you are fluffing. You know, you're not just like dumping. You really want to fluff it and aerate it as much as you can. So you're...
A labor of love.
This is a labor of love. And we loved it. We did it in the garage in the winter. It smells like barn and organic matter. It's steaming hot compost sauna. The pigs at the farm wanted to eat me because I smelled like their food. Put on some reggae and it's a great time. Honestly, everybody was calling, being like, is there a pile to turn today? It was like the thing. It's a lot of fun. So you fluff it as you go down, and if you're doing it with an excavator or a bucket loader, you're also fluffing it as you're putting it down. We have a compost turner, so that's doing it on its own. So the middle becomes the bottom. Then everything you put aside that was on the outside, that becomes the middle. And then the bottom becomes the top. You let it breathe. And you do this until your temperature falls under 55 after several turns. If after like one turn reaches 60 and then it drops off, you know you probably have a moisture problem. But yeah, when you turn, you really want to fluff it and aerate it. The idea isn't to, because we're going to talk, and we're going to make compost extract after lunch. We're going to talk about compost teas and extracts and all that. But you don't need to make tons and tons and tons of fungal compost. And this is coming back to Ruth's comment before, is like, what if I don't have a truckload of carbon to make all of this stuff? You don't need that. You need, 5 times 5 is 25. You need like 25, 30 buckets of carbon to make one pile.
Less is more.
Less is more. Yeah, so you're making one fungal pile, and then the rest of your organic matter on the farm, you're managing as best as you can as like a resource management or an abundance management process. But it's not the pile that's not going to have weeds. It's not the pile that if you've put diseased stuff in there, that it's guaranteed gone. Both are fine. We need to manage our resources. We're talking here about how to make a fungal compost inoculum that you don't need very much of, because we're going to talk about extracts and teas later. And to make one tote of 1,000 liters of compost extract or tea with a nice fungal compost, you need like 3 buckets max. For 1,000 liters, that can treat up to 8 acres. So like we're talking about efficiency. Now the other form of fungal compost, other than what I just described, okay, which is labor of love, absolutely, where you're checking it every day for 2 weeks, temperature, moisture. If you need to adjust moisture, you do that when you turn. You let the temperature guide you as to when you turn, and then when it drops off, you let it mature. That's done in about 6 months if it's temperatures above 10 degrees for those 6 months. In the garage, we just have an insulated garage. It's not heated. It takes 6 months start to finish because we don't leave it freeze outside because it's not a big pile, and having it on a pallet with a fencing means we can come with the jack and just bring it inside and let it sleep and decompose for the winter. Practically speaking. The other method of making fungal compost is much less labor intensive. It's Johnson Sioux piles, which is what the step-by-step instructions are online. That's why I'm not going to go too much into how to make it, because there's a lot of misinformation of thermophilic piles, but that is just step-by-step. You basically... he makes it with just leaves. David Johnson makes it with just leaves, and you put PVC piping in for a certain amount of time to create air structures. You take them out, then you put a drip irrigation to make sure it's at 70% moisture. Outdoors in Canada, it takes 2 years, I've seen. This method was developed in New Mexico, where it takes 1 year. And it's fungal, but the diversity is not as great as what I've seen in really well-managed thermophilic piles, especially in, I think that's a factor because you're just using leaves. So if you were using a more diverse, so if you don't want to turn and you have more time, you could do that method. There is nice fungi, much nicer than any other compost you can buy on the market, so that works well. The nicest stuff I've seen, though, is really from this compost process that I just described to you. But it takes shoulders, it takes time. You choose your moment in the year where you have 2 weeks. It's not 2 weeks where you're only doing this, but you're not going away for 2 weeks. You're at home and you can check every day, and if you need to take an hour to turn your pile every 3 or 2 or whatever, you never really know. The pile will tell you. Then you got to be there, and after that, you just let it sit. But those are 2 ways of having fungal composts, and the reason why we're doing this is to have a bit of basically a probiotic to bring the fungi back into the environments to help decompose, get the cycling process going and rebuilding the fungi in the soil along with the help of the diversity of plants you're growing, right? But this is fungal compost making 101. And when we talk about, there's a lot of talk about native, indigenous microbes, and people are taking forest soil to have indigenous microbes. What does indigenous imply when we're talking in reference to microbes? What does it mean?
Already there.
Of a place. The microbes of a place. When we use, because this is a trend now, they're like, we use native microbes. But all that means is that the microbes come from a place. You don't need to take forest soil to have native microbes of your place. The spores and cysts of the microbes are all over the surfaces of all the plant matter that you're using. So the microbes of your place are on your organic matter. And we, in a compost pile, are creating the conditions for those organisms to wake up and do their thing. So we don't need to go and take forced soil to create fungal native composts. And on a microbial level, like microbes are evaporating off the surface of leaves into the sky. They become the nucleus that water vapor condenses around that eventually create clouds and then blow around the world and rain down, right? So this whole planet is a fermentation station of things going around. The more diverse your ingredients are, and this is the thing I've seen with Johnson's soup piles, the more diverse things are, the more diverse of organisms you will find in it. And the microbes that come from a forest are not what you need in your fields either. All we're doing is facilitating life doing its thing. Yeah, that's what we do. We're shepherds. We're going to talk about what we do with this fungal compost and how it helps regenerate the life in your soils and your plant health. We'll talk about that this afternoon.